Okay, so no one is here. I mean, only Richard and I are here for the call on 2829 at this point. Joe has called in sick and or texted in sick, and Anne, I believe, said that she was going to be out. So it's just me and Richard, and one of the themes that he and I have been playing with every time the cat's away, we start playing with the 60, 90-degree thing. And I'm not sure that this conversation is going to go anywhere because the thoughts aren't clear in my head. But I was just mentioning to Richard that I've written 2 articles about the 60 to 90-degree scenario. How do we get from a 90-degree XYZ 3D axis, which is the standard kind of model of Euclidean physics? How do we get from 90 degrees to 60 degrees and suddenly have a 4-dimensional tetrahedron as a model of universe? And so I'm not even clear that I'm going to be able to recall this, or that's going to be worth keeping the recording. But what I've learned as I've been studying dimensionality is that in order to examine a dimension, the technique is to collapse the underlying dimensions. And by collapsing the underlying dimension, we can then have a 90-degree vertical axis come out. And so let me explain. We take, oh man, one of the articles is coming back to me here. I take I'm going to really go further than I've written. Take an energy field. The energy is everywhere in the field. I pick a particular spot to focus. When I focus on that spot, it becomes a dot. And now I can extend that dot in any direction. And so I grab the dot here and I extend it in any direction. I can go up, sideways, or out on a line. Let's say I go up sideways. So now my little dot has become a single space holder, because a line, as we know, doesn't really exist. It simply denotes that there's some kind of measurable distance between point A and point B. And that even though the line doesn't exist, we're actually measuring outside, and we say, okay, here's the measurement inside. So now, in order to come up with 2 dimensions, we collapse that one. I'm going to go with this idea of collapse and fold. I collapse that one dimension down onto a flat plane. And then what I do is I go ahead and go anywhere along that plane, and I make a line vertically up at 90 degrees. And I can do that 90 degrees because I've collapsed the first dimension. In other words, the first dimension is not anywhere in the field. It's now here in the field. And now I take anywhere along that line, I can place another dot. Now that dot could be a potential second dimension. In order to demonstrate it as a dimension, I simply draw it I just draw a line up. And then I place my dot to end that anywhere along that line that I want to. But I do it at 90 degrees because that keeps the relationship between the x-axis and the y-axis equal. There's an equanimity or an alignment. I almost want to say the word balance, but I hate the word balance.
Yeah.
So there's an equality. There's an equality about it because it is at 90 degrees. Now, if I want to examine, and by the way, if I want to examine and create a model for a 3rd dimension, then what I need to do is I want to take that XY axis that I have, I want to move that dot to the center of the page or to the left side of the page, and I collapse it. So now I've collapsed it so that the first dimension and the second dimension are flat in my 2-dimensional created space. And because those are flat, I can now take another line or come from that dot, that place of observation. That dot is the observer, as Richard has pointed out, and we've examined that always. And I draw another line vertically up from that. And in order to maintain the relationship, I make it at 90 degrees, because that way the there's an equilibrium, there is an equality in the space. Now, in order to perceive all three axes, the X, the Y, and the Z is now coming vertically out of the XY, which is flat, I need to twist that XY axis slightly, because if I don't, I can't see the Y-axis for the Z-axis because they override each other. So I have to not only flatten the second dimension, I have to twist it. So now, let me think here. I'm not sure this is going to go anywhere. I wrote an article on this, and it was really profound because I spent about an hour in bed one morning before I got up, and I was just I was just in a state of hypnagogy about this thing. When I take that first and second dimension, which is at 90 degrees, and I flatten it out, in order to, after I draw my vertical line up, I'm not going to see the y-axis. Now, you get that? Is that very arbitrary, or is that actually going to be a generalized global experience? That I will not be able to see the y-axis because the z-axis is in the same, visually, on my two-dimensional piece of paper, it's in the same space. So in order to see the y-axis, I have to twist it. Now let me think here, because there was some other aspect to this. Whoa, look, here comes somebody.
I was just doing something that I hadn't done before, which is kind of interesting.
Okay.
I took the XYZ axis at 90 degrees,
Right.
and then extended it out to the end of the say Y. And what I ended up doing when I connected the dots, I actually got the side of a cube. And when I went out 90 degrees on the Z axis and did the same thing, I got another. I got the bottom of the cube, if you want. So that,
have you drawn it?
Yeah, it's like if I
I'm
can get
gonna
it.
I'm gonna pin you to the middle here. Okay.
So it's right here, this one. So I started out this with XYZ,
Right.
and then I went to the end of the Y and raised it up, and then I connected it over to the top of the X, and I get this square, like a side of a cube.
Yeah, now you've done the XYZ in a direct line like the way you collapse a tetrahedron. And
Yeah,
because
well, and
most
then
people
what?
just start from the same point on all three dimensions. Go ahead.
Yeah. So anyway, all of a sudden I've created the cube
Right.
with the XYZ if I connect all the lines.
Yeah.
Then what I was working with is if I then take, say, X and angle it to 60 degrees instead of 90, and then I've got to do the same with at the bottom here with Z and
Right.
change it to 60 degrees.
Right.
Then I can hook them all together and
Right.
I'll have the 60-degree angle. And what's interesting, what happened to me, just a minute, throw back here. When you do this, when I did this, I actually did it originally.
Oh, the camera's over here. Good.
Yeah, I did it originally with the X going up and the Y, like, whoops, um, the Y going out to what would be my my right, and the Z coming towards me at 90 degrees. And so when I went through the same exercise, then what happened is the observer ended up in the center of the
Yeah.
tetrahedron,
Yeah.
right, right here. And so now I've got the observer observing the three-dimensional surroundings, and the observer is sitting in at that middle part of the tetrahedron.
Okay, so, and
Wow.
so if the observer is in the center of the tetrahedron, then see, this is another thing that I anticipated when I was in this hypnagogic state, that when I look at dimensions, if I look at a tetrahedron, the faces of the tetrahedron become the four dimensions. And so
Yeah.
the question is, are the faces the representation of dimensions, or are the nodes, are the vertices the indicator of the dimension? And
Well, it's the nodes.
well, if the faces are actually an indicator of the dimension, then the nodes are really just boundary setters. If the nodes are the actual, if we come from the center line and follow along on an axis to a node, so the question is, am I regarding the node as the dimension, or am I regarding the face of the tetrahedron as a dimension? And I went through that
Yeah.
whole process in my hypnagogic state.
Well, what I'm doing when I draw the tetrahedron the way I did, it's still it's on a two-dimensional plane, and so the what turns out to be the observer then is in the center of that triangle.
Right.
And then
But what put the observer in the center of the triangle?
just because of how it draws out on a two-dimensional piece of paper.
Yeah,
So you draw a triangle, so that's easy to draw on a piece of paper. And then you
right,
put a dot in the middle and connect it. So all of a sudden the
right.
fourth dot creates the six interconnections.
But you started with a triangle, and in my thesis, I was starting with a 0 point field. And I created a perturbation to establish the first point as the observer. And in one dimension, that one dimension can go in any direction. That was my premise. And once I decide on a direction, that becomes an axis. And I arbitrarily, from the point of the observer, realize I have to extend the line in both directions, and I arbitrarily terminate the length of the line. And my issue with one point of what you drew is that you're arbitrarily ending the extension of that plane, and that's how you came up with the cube. In my scenario, there is no ending on the line, and the ending is arbitrary, and I come up with a tetrahedron just by taking the XYZ axis and just going out let's say 2 inches on each of the axes, putting a point in those, and then I connect those points. I got a tetrahedron right there.
Yeah, well, and I just did the reverse. If I draw a tetrahedron, um, uh, like that, what is
A
that?
little higher. A little higher, please. Yeah.
Yeah, this one.
Yeah.
Just a triangle with a dot in the middle and then connect them.
Yeah.
Then I just realized that if I take this angle um, and turn it to a 90-degree angle, and I take the other and turn it to a 90-degree angle, then I've returned to the XYZ with the observer at that cross section that we talked about before.
Oh, cool.
So now all of a sudden it's like I've got a way of picturing. I can draw the tetrahedron on a two-dimensional piece of paper, 60-degree angles, and then I can just open it up to 90 degrees, and I've created the XYZ axis, um, and theoretically without the observer.
Yeah.
Uh,
And that's almost what happens with my observation in my papers I've written. Um, because that's the way with a two-dimensional brain, that's the way I'm going to perceive the 60 degrees. I'm going to see them at 90 degrees because all objects are 180 degrees observe each other on a 90-degree plane in a two-dimensional or 3D world. So it's interesting, that last point I come to in my paper, but I'm starting off with nothing. You started with a triangle, and I'm starting with nothing. I'm saying, okay, I have a field. There is no point in the field. How do I create a point in the field? And then how do I expand? And how do I take that point then and fold it and refold it? And how do I come up with 2 dimensions, 3 dimensions, and ultimately 4 dimensions? And in my thought experiment, the way that I come up with it, I collapse it and I have to fold it in order to make it observable. So the 60-degree comes out of necessity to make it observable as 90 degrees in a 3D thing, which you just said coming backwards. And I'm trying to say the same thing coming forward.
Yeah. Well, I
So,
mean, the other thing too, hi, Joe. But the other thing that's just starting to happen with me is that uh, if you start with a point, I mean, if you start with nothing, then you have to enter a point.
well, I don't start with nothing. I start with a field, which is everything.
Yeah, okay. Well, that's
Okay.
so you start with a field, which is everything, and then you put a dot in the field.
I create a perturbation in the field, and that perturbation is the observer.
Yeah, okay, it creates something.
Yeah.
And so it creates the observer.
Okay, good.
Uh, and now if you take the observer and angle out 60 degrees to some endpoint, because you could end up
But but
equal.
but we've pointed out that Bucky says that no two observer and otherness relate only at 90 degrees. That's a Bucky principle. That is your H. Your H is at 90 degrees. And so I took your H and said, okay, in universe, A and B relate at 90 degrees. So you can't arbitrarily get to 60 degrees. The intuitive relationship is 90 degrees. And so then my process was, okay, then how do I get to 60 degrees? And so I started from the inside. And I have a whole thing about the observer. I have a whole thing about extending the line. And I've been not clear on that. So I'm defenseless here. So,
Well, I tell you what I just did then with the H. It's kind of interesting because it's again we've on one of these other sessions. Mark Wagnon constantly talks about both and.
yeah.
So, in other words, it's not the idea that we want to replace 90 degrees with 60 degrees
Hmm.
or vice versa. We actually want to figure out how the two of them can be both and.
That's
So,
exactly what my thought experiment does. Go
yeah.
ahead.
So the H for me is the 90-degree connection.
Right.
So you got that vertical and the horizontal connection.
Yeah.
But if you take the the upright, two uprights of the H and angle them into each other in order to represent the notion of being able to support each other or lean on each other. Um, and so you take it down to the crossbar. So you got a triangle. And then below that, if you angle it in, you get another crossbar or another triangle. And then if you draw from the point at the top down to the bottom, you get a line between, and you've just created a tetrahedron.
Sure you did.
Uh,
But in my thought experiment, I actually just have a justification for going from the 60 to from the 90 to the 60 degree without just doing it as a convention of an accident
yeah,
or constructing the idea that they're going to lean on each other. In fact, all points in a field are completely independent and thus are interdependent because they all exist in the field. Gee, I don't know where Joe went. We could have said hello to Joe. So let me get on my phone and give him a text message. I'm going to pause the recording.
yeah.
So I reached out to Joe, and he was ill. And as soon as he stood up for a minute, he realized how ill he was,
Oh
and
my
so
God.
he went back. Now I can see you've been busy the whole time while I was communicating with
Yeah.
you. What have you come up with?
Well, what I've really come up with is if I start with I'm going to go back to starting with the triangle, but actually I could go back to the field idea and put a dot in it. Um, and then what I can do with the dot is I can extend it up if you want to the X um, axis, and then out to the Y and out to the Z at 90 degrees.
Sure.
And when I do that, and if I said that the dot is the observer, well, the dot is not connected to the well, or perhaps the dot's only connected to each of the vectors, the endpoints of the vectors, whatever they are, one at a time, because they're not interconnected. But then when I take the 90 degrees and I change them into 60 degrees, they can connect, and now the observer is part of the observed.
Cool.
So, and if I started, yeah. And so what I'm doing on one with the tetrahedron is that the angles that come in, like the A shape, I pull them out so that they're 90 degrees. And when I do that, then I've actually created the 90 degree sort of vectors of what could easily become a cube.
Yeah.
And I have no way for the observer to be interconnected with all at the same time. But when I
Well,
put the angles back to 60, then the observer becomes part of the observed.
right. Which is the case.
Mm-hmm.
Um, uh, Ultimately, that's the case. And so what what I'm doing with my hypotheses is I'm assuming that I'm creating the universe one dimension at a time. And so I make certain rules, like when the observer along the x-axis looks out, and to use your model to X, Y, and Z, I probably observe the same distance in the directions unless I have some distorted view, in which case I would make a weird, there's a term as I studied what I was creating, there's a thing called shoot, let me see if I can remember it. I was going to say a trirectal uh, tetrahedron. Have you heard that? Anything like that? A term similar to that? Let me look it up here. Tri. Okay, that's not going to work. I'm going to go definition. Okay. Okay, that's not going to do it. Let me come up. I'm just going to go with tetrahedron. And then what I'm going to do is do it by date because it'll be real close here. Tetrahedron. It's called okay, here it is. I've got it's called a tri-rectangular. Okay, that's a different one.
I looked up, I got tri-tetrahedral,
Yeah.
and I got
What did you find with tri-tetrahedral?
um, well, I got a graphic, and it looks like it's probably 3 tetrahedrons.
So if I look on if I just look on Google, I'm going to find a tri-tetrahedral.
Yeah, that's what I just did.
Oh,
So
here, Joe had put a chat in the thing saying that he was feeling uncomfortable and wanted to discontinue his view. So let me go ahead and I'm going to go ahead and see if I can discover what you discovered. Just share my whole
it's
screen.
also called a boat polyhedron. Kind of
And
looks like a boat.
so it's called a tri what? Tri-tetrahedron?
Yeah, tri-tetrahedral.
Oh, hedral.
There it is.
Okay, whoops, images.
There.
Tri-tetrahedral right there. Okay, that's 3 tetrahedra.
Yeah,
One here, one there, and one there.
and you can see why.
Does that relate to your XYZ thought?
Well, yeah, well, that relates to what I just looked up, and yeah, I'd have to do some more work on getting the. See, there it is laid down flat,
Right.
um,
On 2 dimensions, yeah.
on 2 dimensions. Yeah.
See, with my hypothesis, what I'm doing is I'm playing creator.
1, 2, 3, 4, 5, 6,
And
7, 8. Yeah. You
okay,
can see a tritetrahedron is actually the same in terms of the triangles. It's 8 triangles, so it's an octahedron.
in yeah, yeah. What I found was a thing called a trirectangular tetrahedron.
Oh, okay.
And a trirectangular tetrahedron is a tetrahedron where three faces are the same and one is different. So let's see if I
Right.
can,
Yeah.
I can't,
Yeah.
let's look for images for this. Okay, so that would be like, here's a tri-rectangular tetrahedron right here. And so a
That's kind of what
tri-rectangular,
you and I were getting at the first time we tried this,
right,
because we were getting um, a tetrahedral shape, but it was not sort of 60, 60, 60.
right. And in this tetrahedral shape, in fact, imagine the X, Y, Z axes extending out,
Yeah.
each at 90 degrees from each other, then go up 2 inches on the Y or on the Z, go out 2 inches on the X, go out 2x out 2 inches on the Y, and then just connect those.
Yeah.
And
And
they
that's
become a
exactly what we
tetrahedron.
were doing originally.
Right. That becomes
Um,
a tetrahedron. And the problem of creating a cube there is I have to put something else out there. And by sticking with the tri-rectangular tetrahedron, the observer stays at the
yeah.
convergence of X, Y, and Z,
Yeah.
and we label that point O because
Yeah.
the observer is experiencing the X, Y, and Z in the first place. And
Yeah.
the observer cannot experience X, Y, Z anywhere but at the crossing of
Yeah.
those dimensions.
Yeah, well, see, what's really neat about that too is when you put in the tri-rectangular, so the rectangular by definition is going to be 90 degrees.
Right.
And so you get three, 1, 2,
Here's X, Y, and Z.
yeah. So you've got two 90 degrees or
I got three 90 degrees. There's 90 degrees between X and Y. There's 90 degrees between uh, Y and Z, and there's 90 degrees between Z and X. So there's one here, there's one here, and there's one here. Let me see if I can actually draw that. And then this green thing is where I take the XYZ axis and I cut it in half. Or I just
you,
arbitrarily draw a point up
yeah,
because I'm going to say as an observer, I have a limited space of observation. My eyesight is only so good that I can see 2 inches up on Y or on Z. I see 2 inches out on X and I see 2 inches out on Y. So the black dot becomes the observer and the green dots become the extensions of X, Y, Z. And the three of those faces are exactly the same size at 90-degree angles, and the green space is different. That's called a tri-rectangular tetrahedron right there.
yeah, yeah. Um, and as you say, in terms of an XYZ axis, um, heights, widths, and lengths. Of course, you can be in a room that's 10 feet high and 4 feet wide and 50 feet long.
Yeah, but a human being created that room. And in my thought experiment, I'm saying, hey, I'm God and I'm creating dimensions here.
Oh yeah, you can.
And so I have no context in which to say there's a cube or anything. I have to start with energy on a plane, and then from the observer describe reality. So here, this vertical line, that's the x-axis. Here,
Right.
let me. You can see that.
Yeah.
Yeah. Okay. Good. Because I think I'm going to have to if I write this up. This is part of what I put together, researching out what I did from my thought experiment. So O is right here at the convergence of X, Y, and Z.
Hmm.
Yeah. Okay. So that's
And you see, the other thing that we were trying to do, or at least I was, when we first started out, I was trying to say that what we were having to, what we were creating with the 90-degree angles was, well, I called it irregular tetrahedron. Now I find out that because the 90 degrees were kept, it's really a tri-rectangular tetrahedron. So the name itself tells you that it has to have some 90-degree angles in it. Um,
well, and yeah, rectangular.
yeah,
It assumes 90 degrees, and there are three 90-degree angles in there, right?
yeah. It's interesting why I can't see that third one.
Okay, let's see if we can expose those. And if anybody actually dares, if we actually publish this, if anybody dares um,
Hmm.
view it, they're going to probably need all the extra time just to figure it out. All right, so let me see. I'm going to come down here, and I'm going to, in my thought experiment, O is a requisite. O is the observer on the
Yeah,
in space on the field. And as soon as I become the observer, I'm the perturbation on the field, and I am O. So there's O right there.
yeah.
In fact, I'm going to change these to I like the Calibri font. And I've also got myself a mouse, and I found out when I started getting a mouse that the things started to work better.
Oh,
Okay,
good.
so there is O right there, and then X. We're going to say this guy up here. I'm going to get as close as I can without getting too close.
Yeah,
This is Y,
right.
and then, or no, that's Z. That's the third dimension because X and Y are the first two dimensions. So arbitrarily, this becomes X or Y. And then this becomes,
Yeah, like my eye goes clockwise, so my eye would say I'd start with X at the top there and then go over to Y and then to Z. So, but it
well, and
doesn't
I,
really
I
matter.
see your perspective there. The trouble is when in conventional geometry, we always start with the X and Y on the flat plane and we extend the third dimension up, usually.
Oh, I see. Okay, I see what
Okay,
you
but it doesn't have to be that way. But usually, if I'm and what I'm doing is I'm thinking that doing a graphic where I start from zero and go out, and my first one's going to be X, and my second one is going to be up from that. It's going to be Y, but then I
right.
flatten it down in order to take my third one up from there, my Z or my Z. So there
Hmm.
is a tetrahedral thing, and what I'm saying is the reason why that green spot is in each one of those places, the reason why the X um, vertex is in X, and the reason why the Y vertex is at Y, and the reason why the Z vertex is at Z, is because having created these, which thought experiment I haven't explained very well, my observer has a sphere of influence. And as soon as I draw that sphere, the sphere has a radius from O, from observer. And
Yeah.
so that the radius, all these lengths from 0 to X, from O to Z, from O to Y, and O to X have to be equal because there's a sphere of influence. And I see it as a circle of influence or a sphere of influence. Circle on
Hmm.
2 dimensions, a sphere on 3 dimensions. And then when I connect these lines, these points, because that's the end of my observation, bam, 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 and then realizing that in spherical geometry anyway, these aren't straight lines, they're curved lines. And so suddenly I've created that spherical tetrahedron, right?
Well, yeah. If you take all of those straight lines and push them out a bit so that they're curved, then
Exactly.
you end up with a circle.
Yeah, and I end up with a spherical tetrahedron, which is
Hmm.
more, um, geez, I would have thought that Wiki would have given me a spherical tetrahedron. Oh, it just gave me a tetrahedron. So I got to go back to Google and I got to go to a I got to go back to Google and
And
then I need to
anyway,
say,
these are really interesting because it really expanding my mind to sort of that all these different versions of a tetrahedron have their own proper names, if you want. Uh,
yeah. Well, that's what
eh,
I started doing. Once I started drawing these things, I go, is there a name for that? That's how I
yeah,
found a tritetrahedron. You know,
right.
I went into Google, I said, what is a tetrahedron that has uh, three equal faces and a not and a fourth face of different area? And I came up with tritetrahedron.
Wow.
Okay, so here is Google gave me tritetrahedron. Okay, so here is, see, I'm getting, that's the little guy I just drew right there. I just drew a D. This is not nice. I got to find a different picture than this. Let's see. There it is right there. There he is. That's the guy I'm looking for.
Oh, for God's sakes.
What
Let
is
me tell
that?
you about that shape.
This is called the Renault. What the heck is this called? Richard, tell me about that shape.
Well, um, at a local farmer's market,
There it
you know,
is. See? The
yeah.
Rouleau. The Rouleau tetrahedron. Go ahead.
Well, at the farmer's market, uh, a pottery guy, ceramics guy,
Yeah.
was making all kinds of different uh, pottery shapes, and one of his favorites is to make it was just sort of a little not tetrahedral, but sort of triangle kind of rock face,
Yeah.
and he put he has some kind of rattling in it, so it's called a rattlestone. And then I was chatting with him, and one day a few years ago, and I said, "Geez, do you want to make a fortune?" Because every time I see uh, straight edge tetrahedrons in pottery form, um, that well, actually, I don't. I said to him, you know, you could make a tetrahedron because he understood what tetrahedron was right away. And I said, you know, if you made a tetrahedron ceramic or pottery, they should sell like hotcakes, and you'll make a fortune. So I went
What
out
is,
there again, you know, several months later, and he actually had made in pottery form that shape, that kind of tetrahedron.
and did he, had he been, was it a bestseller?
No, he said I was the only one that bought one.
Oh, dear me. You have to send his address to all of us and we'll travel to Canada and go find the guy.
Yeah, go and get one because
Yeah.
he, he he said the hot cake sort of phenomena hasn't happened yet, but it's um I've got the that particular shape in on a pottery shelf. I'll have to get it or go take a picture of it. And it's amazing because it's exactly what he made. But he said, you will not believe how hard it is to make that shape in the pottery.
Really?
Yeah. So that was another
R-E-U-L.
reason he gave up on it, 'cause the labor was too
Huh.
expensive.
I hate that.
Yeah.
Realeau.
Yeah, that's sort of
There it
Relu.
is here. And this is I found one
There's
where,
an X in there too, AUX.
yeah, well, French people do that a lot.
Yeah.
There's one that I
Yeah, so
have.
that's what he did. He had to just push out the edges and give them a curve. And of course that to me is you know how the teepee ends up being with a circular base,
Okay. Um,
or how the sweat lodge, you know, ended up being sort of a geodesic dome type of structure.
I also found out that a tetrahedron with 3 equal radii in one dimension and 3 equal radii in a second dimension is called a dysphonoid. Specifically, it would be classified as a tetragonal dysphonoid. A tetragonal dysphonoid. If the triangular faces are isosceles triangles with either side with equal side lengths in the 2 dimensions with equal radii. See that these things need to be in 3 dimension. And so what I'm going to do is I'm going to, because I've done this before, I'm going to go and put this here, and I'm going to Google and say, I'm going to go animation, because I've seen an animation of the
Oh,
Rouleau tetrahedron before. Here it is. This is it. And it's in Wiki. This drives me crazy. There it is.
yeah,
And so this is the Rouleau tetrahedron, but it is equal, it's equal
yeah, yeah,
equilateral triangles. So this is
yeah,
4 equilateral triangles.
yeah,
Technically speaking, mine is not. Mine is, we have
yeah, but,
3
yeah,
equilateral triangles, each with a 90-degree vertex at the top, and then a obtuse angle on the sides.
yeah.
So, and then that creates the face right there. So I'm gonna do this. Any other thoughts you have while I'm screwing around with the mechanics here?
No, I'm just excited at the fact that what I have on my shelf in another place is exactly that, and that's what he made. And and so I see what he was getting at. He had to take sort of a triangle structure that he was working with, and then try and curve out the edges,
Right.
and then you know put it into a pottery oven and create it.
I've got to catch this just at the right angle where it's, yeah, I can't catch it where it's there. Oh, shoot, that was it. There we go. I'm going to capture this picture
Mm,
and I'm going to put it, let me see, this is, I'll call this Rouleau tetrahedron. The one thing I've resolved my mouse problems, you know,
yeah,
Rauleaux tetrahedron, animation 1.
and take the N out of
Oh,
tetrahedron.
I'm gonna have to do it. Yeah, shoot. Thank you. That's my problem is I need an assistant by me constantly because I'm just absolutely fly by the seat of my freaking pants. And then I have to go back over and correct everything when I'm done. So there's that. And then let's see if I can capture it. Okay, that's a good capture. So there's another view.
Yeah,
And let's see. I might be able to REAEAU. And we're going to call this number 2. But you wanted me to, you captured, what's the, oh, I forgot the X, right?
yeah, on that one. And the other one, you had an extra N in the tetrahedron.
Oh,
You had TRANHEDRON.
oh, well, it's not going to give it to me. Here we go. Okay. Is there everything spelled okay there? Tetrahedron
Yeah, yeah,
sphere. Okay, good. There's 1, 2. And then, so there's another one. Well, I want to put that down here on the page. Where's my page? Oh, it's up there. So, oh, crud. I wish that I were so much faster at this stuff.
yeah. This is great. Well,
And again, if I use my mouse here, it would work better. I've discovered that the mouse gives me the precision that I'm unable to get with my finger for some crazy reason.
Yeah.
And then here's rouleau. I think that was rouleau 1. So here's, we'll do rouleau 2. Oh, that was rouleau 2, so we'll do this one. This is rouleau 1. Well, that's the wrong one. I thought that I had okay, first thing I want to do though is grab this guy and put it out here. So that's the animated guy right there, just for the heck of it.
Yeah.
And then let's come back over here. What is this one? That's the one I got there. All right, so now I'm doing what I can to find a different one of these. Where's my, there it is. Okay, good. And we're going to go with this. Not quite. It's really random. I have no control over this thing
Yeah.
because I can't. Oh, you know what I could do is maybe pause the. I can't pause the animation. I can't pause the animation. So it's simply a matter of hitting the button and hoping it stops in the right place. There
Yeah.
we go. That's the one.
Oh, okay. Yeah.
So now it kind of looks like a, now it looks like it. Now I think most people can see the tetrahedral
Yeah.
aspect of it. REAL, there we go. And it's number 3. Okay, good. And then I'm going to take this guy and post it down here. Okay, well, now okay. And so I'm going to go back into the dialectic here, okay? And sound a little argumentative. So what most people tend to do is they come out here and say, oh, well, this is a cube because they put another dot out here somewhere, right? And they
Yeah.
say, oh, yeah, here's a cube. I throw a dot out here and I throw a dot over here and I throw a dot. But
Well, what you do at what you do at Y
yeah,
is you instead of having the edge angle over to the Z, it goes straight up in a 90 degree.
okay, I don't understand. What's the it that goes straight up?
Um, well, the green line there between
Okay.
Y, X
Yeah,
and
but
Y,
see,
it
but
just
I
goes.
don't have, but under that premise, Richard, I don't have any logical reason to place another dot out there. I mean, the observer starts
No,
in,
no, you don't. Well, yeah, you're right. You don't have any logical reason,
yeah,
which is another perhaps argument as to why the cube is really a fiction of somebody's imagination.
that's exactly right. It's a fiction of my 3D, my 2D brain, which has all these 2D pictures lined up. And because my brain, my eyeballs, my brain focused on them at different things, by the time I'm 3 years old, I realized that this picture is in front of that picture and that picture is behind that picture because how soon I bump into it and I hurt myself. Does that explain it?
Yeah,
Does that create a picture? Yeah.
yeah, and the other thing is that um, that if we start from that place where you can actually see a connection that can go between X and Y and X and Y and Y and Z and O and X and O and Z, um, and you get that created space. But in order to do what we were taught to do, is that, as you say, you're going to have to add in 2 more dots, um, and um, and you're going to take up a lot more area or space. And you get back to what Bucky says is that, you know, nature is more efficient than man. and and so nature is more like what we've got up there in terms of the O is the observer, XYZ, whereas man-made turns it into a cubical sort of structure and forces 2 more dots to be created from God knows where.
Well,
And
Yeah,
Yeah, and then connect them so that you end up with what I was having earlier. You would end up with an upright face of the cube, and you would have um, a bottom face uh, with the cube, the two squares, and they're theoretically connected to each other like a hinge. But that's all
well,
wasted energy and wasted time and unnecessary dots.
exactly. So in this particular example,
Yeah.
if I'm going to, because I will do a podcast, I will do a recording on this because this is, to me, profoundly critical. Because I want to create space without using my imagination. In other words, I want to create space. Let me see, I'm going to put Y over here. This guy here ends up being the green line, and maybe everybody sees that, but just to make sure, this guy here is the puke green line. So we'll make him big so he can be seen, and then we're going to make him, I'm going to make him a little bit bigger than that. And then we'll make him puke green. Lime green. Let's see here. How do I get lime green? That's pretty close. That's pretty close right there. So,
Mhm.
and then X is over here. Boop. Okay, so there I have now, here's O, X, and Z or Z. I'm trying to be respectful to my
Right.
friends. And so then what we end up with, if I'm going to continue this down here, is I can do this becomes an equilateral triangle, I do believe, because a squared plus b squared equals c squared, the line connecting x to y and the line connecting x to z are the same width because the other
Yeah.
lines are the same. So using that formula, the green triangle becomes an equilateral triangle by logic. Now, can I assume that correctly?
I think
Or,
so. Yeah.
yeah. So
Yeah. As
this
long
is,
as the vectors are the same length, then it's what it should be.
yeah, good. So, good. Bam, there we go. All right, so now I can do another, let me see, I'm going to get rid of some of this stuff down here. Wow. Boop. And then I'll take this guy up here. Boy, this is so much better than having I guarantee you this is so much better than using and if I had an actual mouse pad instead of the book I'm using, I think I'd actually be in better
Yeah.
shape.
You would be.
Okay, so I bring this down here and I'm going to just temporarily move this over here so I can slide this puppy this direction and then come back out here and slide this back out. So then this becomes, I'm going to move this in a little bit. So O is there, Z is roughly up here. Y is down here. And X is over here. Beep, capital X. So there's X, there's O, and there's Y. And I could take and draw a vertical line here. And this becomes my Z to O plane or my Z to O vector. Okay. So there's my, and I'm going to take this and get it out of the way. Well, that's interesting. Okay. Okay, and this is a key points about dysphenoids. A dysphenoid is a type of tetrahedron where all four faces are congruent triangles, meaning they have the same side lengths, but not necessarily equilateral triangles. Very interesting. See, I can't even picture that in my brain, Richard.
Well,
I
I'm trying to
can't even
picture
see that.
where they come up with the word dysphenoid.
Yeah, dysphenoid.
If
Congruent
I
triangles.
was putting that in sort of a handout for students, um, they would mispronounce dysphenoids and tell them that they were dysannoyed with me as the
Yeah.
instructor.
Well, you've already had the sad experience of dysphenoiding your students in the past.
Yeah,
I love your story about the
yeah,
Christmas tree decorations, how your student tried to flee from your incessant conversations about the
yeah.
tetrahedron and only goes home to find themselves um,
Yeah,
uh,
I have an image of sitting in that church room, um, and her friend or sister saying that you can be an occupational therapist all day and get your mind off of what you just experienced for 4 months at the university. And the poor woman is, I mean, it must have been torturous
yeah,
for have to make those damn shapes. I don't know how many she made in an afternoon, but I'm sure it was more than one. Well, in fact, I know it was because she came back with two and threw them at me in my office in
right.
January. And I still have one of them. I wish I could meet her again someday.
Oh, that would be so wonderful.
Yeah.
I um I had an experience that was kind of similar to that, where I went to a class and I had learned something in a class. And in my previous class, I had a very excellent teacher. And I went to the special study group thing for youth. And the guy who was teaching that class did not make the point. And I raised his hand and said, well, this is actually the situation. And the teacher couldn't grasp the idea.
Right.
And so, I ended up losing. I looked like an idiot to everybody. But um, I'd like to find out where that X is. I know how to get there to that. I have an extra X over there for some
Yeah, I
reason.
see that. Yeah.
And so the way to get there is to go up here like this. Then I can get in here and do this.
Right.
I thought I could have slipped by this, but
No, those boundaries get in the way quite often.
the boundaries get in the way.
Yeah.
Okay, so now we've learned about tri-rectangular tetrahedra. And this was the result of my um, epiphanies in a hypnagogic mind experiment.
Hmm.
Why are these all screwed up? There should be Z up here, X down here, O over here. And where is Y? Y is, oh, I could extend out a Y. So that's what I need to do is I need to build a Y. And the Y would be like this. This is
Oh, yeah. Okay.
your standard conjugation of linear dimensions.
Hmm.
Oh, where did that go? Okay, there it is. Oh, and I could have gotten this much faster. So, okay. And then we're going to just double that. That's what I could have done last time to
Yeah.
make it go faster.
I forget to do that too. I can
Yeah,
copy and paste
a lot faster than I
line,
can grab a line and extend it.
yeah, line after line. Copy and paste, and then I stretch it to whatever length it needs to be.
So that kind of is a representation then of,
Yeah, yeah. I mean, it's and what a neat way to be able to get from that OZX um, sort of rectangular triangle and then factor in the W or the Y and connect the lines. And it doesn't take much to be able to see that that's an irregular tetrahedron or the rectangular, tri-rectangular.
rectangular, yeah. To coin a phrase, right?
Yeah.
Having learned something, we don't want to unlearn it too quickly. So let me just do this. I'm going to make sure this is my favorite font. I have never been able to figure out how to get Word to default to that font. But let me see. So the angle, what's the mathematical sign for an angle? I have no idea. So I'm going to say, I'll call it L because that looks like an angle. Okay.
Right.
So equals 90 degrees. And I'm just going to list all these 90-degree guys down here. 90 degrees is Z, O, and X. It says L equals angle. And I'll do this, and I'll do that. I'll copy this 3 times. And we'll say, to clarify to the universe, L equals angle. Okay, then L at 90, and I'm going to just also get rid of some space here so that it jams in a little bit better. Okay, good. Okay, so, and so the first one is ZOX, the next
Yeah.
is ZOY,
Right.
and the next is ZOY, ZOX, and XOY. And now I've identified all of my angles, right?
Yeah, that's what I'm wanting to see.
Okay,
So I
so
see that one and oh, wait a minute. Yeah, okay.
I
X,
think I can make
X,
this a little bit
X, O,
simpler.
Y. Okay, I see that. X, Z, O, X, and then Z, O, Y. Yeah. Yeah, that should get the 3.
Good. And so that simplifies it. I tend to over-explain things, but now I've got the least amount of things. So now the question is, what are the angles of X, Z, Y? So it's an they have to be 60 degrees because that's an equilateral triangle. There's your 60 degrees. That's how you get a 60-degree. That's one way of getting 60 degrees from 90 degrees right there.
Yeah, like if you have how many of those angles are there? 90
There's 3 of them.
times 3 is 270, and 3 times 6 is
So if we measure
oh, that's
X, Z, Y, we have 60 degrees. And if we measure ZYX, we also have 60 degrees. Oop. And if we measure XYZ, XYZ, yeah, XYZ, which is interesting that we actually have an alphabetical anything. X, Y, Z equals 9. And that covers all three angles, right? X, Z, Y. And I think to keep things sane and so people don't go crazy, we should go, oh, we did. X, Z, Y, then Z, Y, X, and then Y, X, Z. And now we've got everything symmetric and it's not going to drive people too crazy. Whoop, that's got to be 60. So that's one way to get from 90 degrees to 60 degrees, Richard.
Yeah, well, and it also is for some anyway, is a way to have both and.
Yeah. Oh, I see. And I've got to come down here and give myself I think I had supposed to be a Y right here. I don't know what happened to it, but I'm going to put it in there. Okay. Well, that's curious.
Well, again, on the bottom one too, I don't know. This is where again, if that zero went into the middle, the observer into the middle.
Yeah. I don't mind doing that because then we could have
And
we could
then the
show the
other,
entire tetrahedron.
yeah,
Exactly. So what I'll do is come up here. Whoops, that's the wrong place. I'll come up here, put in an O. I'll get this guy here, make him shorter. And then to avoid the other issues, I'll do what I didn't do before.
yeah.
And this is where if I use my mouse, I wouldn't have that trouble. Because my touchpad seems to go a little bit too far, but the mouse,
Yeah.
I hate to use a mouse. I've always hated using the mouse. There we go. And
Yeah.
then then I get rid of this guy and life is
Yeah.
good.
Oh
Uh,
man, that's really geez. Um,
Good. And I guess really to make it really cool, probably what I should do is break this table up here. Oops. And I should bring it down here. And then this guy is down here with this guy where he belongs more productively. And then I can take these out of here.
oh yeah, I see what you mean. Yeah.
And then and then I can, whoops, and then I can put this down here to kind of explain those two triangles.
Yeah.
And then this guy down here explains that triangle. Oh, I'm having trouble now with this mouse. Maybe it's not the machine, maybe it's the operator.
Or the book that you're working the mouse off of.
That's exactly right. It's the book's
The
problem, I'm
pad,
sure.
the mouse pad.
It's the mouse pad, yeah. And actually the mouse pad is actually moving under my hand, so I think that is part of the problem. I'm going to move this over here to kind of line this up. I don't know why I'm such a persnickety dude because, oh my gosh. So if I take this is on top here. And then I take these things and I make these a group.
No, I'm going to be right back here. Just a
All
minute.
right. Um, Okay, there we go. Okay.
May I say something?
Yeah.
X, Y, and Z is you, Julie, and I, and the O is God.
This is on a recording for a minute. And what I wanted to do is just bring these more into alignment here. Okay, Richard, can you think of any thing you'd like to do with what we've got in terms of what any ideas coming up to you?
Well, I really I really like the integration that we've come to in terms of being able to do a both and in terms of 90 degrees and 60 degrees. And it really is well, it's an integration for me. Instead of sort of saying, well, the 90 degree sort of XYZ axis is wrong, and the other one is right, the 60 degrees, which is really perpetuating the binary notion that one must be right, the other one's wrong.
Right.
And this way, I think we've actually figured out a way to insert the observer at the intersection, and then show how you can get a rectangular, tri-rectangular tetrahedron, or you can get a um, what would be a normal, or what's the word I want? um, well, I can get a triangular tetrahedron. That's what I want. Um,
An
with
equilateral tetrahedron, a regular tetrahedron.
Yeah, a regular tetrahedron, um, which by definition is a 60-degree angled polygon. Yeah,
Yeah, at every angle.
yeah. Um, and so, and again, I think what we're getting at is, um, if you've got just the original XYZ, um, and without a real label at the intersection, at the start point, if you want, then there's no way to, you actually have created an observer separate from the observed phenomena. The O has to be out somewhere all by itself, as if
Right.
it's independent of in its observation.
And you're saying that it's appropriate to not have that case? Is that what you're saying?
Yeah, well, I think that's I mean, if you had the zero out away from the XYZ coordinate, then you've got a Newtonian, if you want, kind of model, or you have the the machine metaphor model, or the scientific, the myth of scientific sort of observation separate from the observed. Um, and the notion that that is ideal, or that is non-biased.
So,
and
so
and
restate what you just said, please.
well, I'm just saying that I think what we've done now is to show that you really can't separate the observer from the observed, and if you try to do that, then your map is not reality.
Right, exactly right.
Your map
Yeah.
is not the territory, or your map
Exactly.
is
It
not the
never
field.
is. It never is anyway, but that certainly seems to prove that point.
Yeah, yeah, it's even more so.
It's even more so. And oh my goodness. I should have put those two together before I moved them.
Yeah, I've had that happen too, where
Now my machine's not operating function properly.
it's not, yeah, it's not allowing you to pick up the
My
line.
mouse is dead.
Oh,
It's not allowing me to pick those up. See if that's true with my, yeah, it's true everywhere.
yeah.
So my mouse,
Actually, if you took the other shape and then captured it and moved it back, you,
yeah.
you would probably get them to match up.
If I did what?
Well, if you took the square angle triangle there and highlighted it and then moved it down.
Yeah, it's not letting me highlight anything.
Oh, okay.
So I think what I'm going to do is I'm going to save. I can't even click on anything, and I can't even click on anything. Look, it's not even allowing me to grip that thing right there.
Right.
Let's see if it's allowing me to do anything with this. You can stop sharing. Yeah, good. It allowed me to stop sharing. Now I'm back into my, but it won't let me click on my document. So I'm gonna, oh, but it is allowing me to close the document, or at least you can't see it, but the red line is, it's highlighting, but there's something else going on here. So let me close some stuff down and see what's in the way. I should pause that recording just because this is a complete, utter waste of time. Pause. Okay, so it's now working. So I was able to grab these, the OY and the OX axis. Um, and now I'm going to group that with that. Whoa. And with that. And so let's see, is that included? Wow, it doesn't want to grab that one now. I see, because it was over it.
Hmm.
And I know what's going on there, so I need to send it behind. Now see if I can grab that guy. No. Hmm. Wow, that's interesting. Oh, that's because that's why I wasn't able to grab it, because I have that layer on top of that.
Oh, right.
So that now I can grab this. There we go. I'm grabbing that, so now I can group that, and now I can throw this back on top of there. Whoop. Okay. I have a bunch of room off to the left-hand side of that thing. I didn't operate that
Yeah.
very. It will take me a few minutes to correct that, and I don't want to do that on your time. And it seems to be, functionally, it's allowing me to get around on it, so. Okay, so that ends that. Any other ideas or any other kind of thoughts you want to pursue?
No, this has been great. That's
Yeah. Okay, good.
also to
What's that?
Well, just to have the the connection to the spherical tetrahedron pottery that I have.
Ah, cool. Did you hold that up in the pic in your, do you have
No,
access to it?
I don't have it here. I've got it in
Okay.
another place. So
All right, cool.
and
Okay, so there's your tri-rectangular tetrahedron. And in my thought experiment, this 60-degree relationship evolved out of that thought experiment. And you know, one thing more we could do here is we could take it one step further and I could draw the obtuse triangle ZOX, which by the way would be equal to, yeah, let me put this over here.
oh, that one, yeah.
Let's draw that one and then we'll call it quits. And if you think of anything that you think would be wonderful, let's examine it. I'm going to take my margin here and move it over. Cool. I'm going to take this and move it over here. Problem is I've got my Zoom stuff in the way. And I can put that there. Whoops. I'm going to shrink. Let me bring this over here and shrink it. Yeah, so that goes up there. Special case, a rectangular. Special case, a regular tetrahedron is considered a special type of dysphenoid. Isn't that something?
Yeah.
The regular tetrahedron is considered a different type of dysphenoid, where all four faces are equilateral triangles. Very complex stuff here, not relevant to the effort to develop the 90-degree thing. What is that going to tell us? I thought it was cool, but I didn't think it was relevant. Tetrahedron. Oh, this is cool. A regular tetrahedron is described as the classical element of fire.
Yeah, I was just looking at that on my phone as I was looking up the Rollo, and then
Yeah,
I've got the several images of the fire, and it had to do with three um, elements like oxygen, nitrogen, and then
right,
in the middle it talked about a chemical reaction, and
right.
and they all have to be there in order for the fire to manifest.
Yeah, so let's go into Google and let's go into Google. Not Google, but Google. And let's put in here classical elemental polygons. Are they polygons? 5 platonic solids. Earth with a cube, air as an octahedron, water as an icosahedron, and fire with a tetrahedron. Are you hip on that?
Yeah.
Wow.
Yeah, and there's a couple in New Zealand, man and
Yeah,
wife.
you introduced me to those people.
Yeah,
I came on your trim tab call or whatever.
yeah. And so and we just reconnected here the other night on another talk, but they're working with the tetrahedron in terms of these basic elements.
Right.
And they're doing it in a way that's quite different than what I've been trying to do, but they're using those four elements of earth, air, water, and fire in a tetrahedral configurations.
Yeah.
And they're using it too to do, if you want, organization or business kinds of consultations.
Yeah. That's what impressed me so much is they're actually doing corporate consultations, having this much fun.
Yeah,
How can you have this much fun and be involved in business, Richard?
yeah,
I mean, business is boring and anti a lot of stuff. There's a band named Ghost that uses classical symbols for the band members of Ghost. This is an Emmy award-winning heavy metal band,
Oh,
and my daughter plays bass, and she toured with them. So here are the 5 symbols typically associated with the lead guitarist. Fire was the lead guitarist. Water is the bassist. My daughter Megan was Water, and that was her name. So shoot, I would be remiss if I didn't put this down here in my research. And I'm going to take this symbol as well. What is that?
yeah, that's neat.
Oh, there we go. And so these are the, woo, what just happened? Come back, come back, come back. Ooh, here's your pentagram down here.
Yeah.
Not, there's a kind of, are we devil worshiping now? What's going on here?
I don't think so.
When Mephisto, when Dr. Faust was going for, was trying to learn, and he got all, have you read Faust by Goethe?
No.
It's classical German literature, and in it, Dr. Faust is this genius guy, and he loves knowledge, and he has a limit. He finds his limit, and so he prays to God and says, God, you got to tell me more. I want the answers to the universe, and God doesn't answer his prayers. So in frustration, he starts studying the occult, and eventually develops a relationship. He creates a pentagram on the bottom of on his laboratory floor.
Yeah.
And does this occult chant to trap the devil. And the devil gets trapped inside this pentagon on his floor. And so now he starts asking the devil a bunch of questions. Well, how does this work? How does that work? How does this work? How does that work? And the devil is trapped there. And he keeps saying, well, if you'll answer my questions, I'll let you go. And of course, Faust keeps asking questions and he never lets him go. And the devil's getting more and more frustrated. And finally, after like 3 days of this bantering and having to answer questions for Dr. Faust, Faust falls asleep. And when he falls asleep, the devil conjures up a mouse to come into because the floor is made out of wood. The devil conjures up a mouse and has the mouse eat one of the angles, the vertexes off of the pentagram, and thus the devil's able to escape.
Can escape.
Yeah. But Faust is relentless and finally captures him again. And this time Faust has got it figured out so that he's just not going to let the devil go.
Yeah.
And so he really has it rigged, and the devil's trapped. And so he makes a deal with the devil. Gee, that's interesting. I know why, because I didn't make this a 0. He makes a deal with the devil that the devil will serve him as a servant, answer any questions he wants, and that Faust will live forever. It's kind of like Daniel Webster and the devil.
Yeah.
And Faust will live forever until he finds something of interest. And if he says to the devil, if I experience anything where I say, hey, let me linger here to see what this is about. I don't get this right off. Let me just linger here. And so the devil says, oh, that'll be easy. 400 years later, and Faust has driven Satan crazy. He's reclaimed lands, he's murdered people, he's seduced virgins, and he's committed adultery, and he's killed people, and he's acquired all this wealth and all this land. And he's just completely bored with it all. And he's sitting on his porch one day thinking, man, this sucks so bad. I'm gonna have Satan here for another 400 years. We're not getting out of this. And And all of a sudden, he sees this parade of people coming down the street. And uh, he wonders whether he should conjure up the devil and bring in an army to protect him. But these people seem to be carrying things on their heads and things on their shoulders and things in their hands. And he says, well, let me see what's going on here. He's not afraid because he's got the devil as his warrior, you know. And
Right.
these people walk up and they say, Dr. Faust, thank you so much for the livelihood you're giving us. We live in bounty. We live in safety. Our children are growing, our grandchildren are growing. Thank you so much. Here are all these gifts. And they just lay them on his porch. And Faust goes, what? I have been torturing these people. I have been using these people, and they are grateful to me? What is that about? And he goes, hey, I want to figure this out. And as soon as he said that, Satan appears and Faust dies. And Satan takes Faust's soul in the form of a moth and he's about to put him in his pouch. And I'm getting chills. Richard, thank you for
Mhm.
letting me share this story. An angel of the Lord appears, says, hey, Satan, what are you doing? He says, I'm taking this son of a bitch. This guy is the murderous, adulterous. He is the scum of the earth. This guy, if anybody deserves to be in hell, this guy deserves to be in hell. I'm taking him where he goes. I'm fulfilling the contract. And the angel says, no, no, you aren't. He says, as long as a person, auf Deutsch, in German, it's immer streben. As long as a person continually strives, they aren't
Mm.
yours, they're mine.
Mm.
And Satan collapses, and the angel takes Faust's soul and goes to heaven with it.
Yeah.
And I've always loved that story. That's such a profound story. Now, how the heck did I get there? I don't know. Oh, yeah, the pentagram.
Well, it's
Well,
another part of the of being able to stay with the basic integrity of everybody.
you know,
And we were talking about that today on another one of the sessions I was on. But uh, and it's impossible these days, I guess, not to slide into a little bit of politics. But uh, um, I remember years ago when I was in class with students, and we were talking about this idea that a social work type person has to believe in the basic sort of humanity, integrity of everybody. Um, and everybody's saying, yeah, that's me, all right. And then saying, so here's the litmus test. Because when we say everybody, that includes, and in those days, it was all the atrocities that were going on in Uganda with Idi Amin. And I would say, okay, put him in the equation now and tell me that you still have this belief in the integrity of the human being. And that's when, things like, oh, well, wait a minute, there might be an exception, or students realizing that just to mouth the words that I believe in the integrity of everybody is easy to say, but hard to sort of live up to.
and it was Jesus's message. That was the message of Jesus.
Hmm.
Even if you do it unto the least of these, you do it unto me.
Hmm.
Everyone is divine. Everyone has the opportunity, should be given the opportunity to be at 90 degrees with every other
Yeah,
entity.
yeah,
Absolute equality. And I looked for a word. I was going to say equanimity, but it's really a sense of equality. You are me,
yeah.
I am you, you and I each are Jesus. Jesus is God. And if we develop that kind of love, in John, I've been doing this study for my book, and John says that Jesus says, God is love.
Hmm.
And there's the tetrahedron right there.
Yeah, exactly.
God, Jesus, me, and you.
Mhm.
And there's no equivocation.
No, and then I always do it too in terms of the word. Um, it's a tetrahedral word. LOVE.
Oh, yeah, cool. I
Mm.
love it. Really good. Well, it's 11, we're approaching
Yeah.
our 0 hour. Got any takeaways tonight before we go?
No, I'm taking away the images of these the both and in terms of 90 and 60 degrees, and the actual visual image of how to get there.
Yeah,
And how to move away from there if you want to go back to a pure sort of
yeah,
90-degree XYZ axis. And in my own mind, it's like when I do flip it back into the 90 degrees, I kick out the observer.
mhm.
Mm.
You know
Uh,
what we didn't do? Oh, keep going. I don't want to take away from your
yeah,
technical.
well, so anyway, what it's doing is that the XYZ axis is that if you want an anchor into um, the pre-20th century science is how I keep describing it. And the 60-degree angle is a reflection of the unfolding of 20th and 21st century science. Um, but the trap you get into is if you're being critical of pre-20th century science, you're on the verge of also wanting to dispense with it, throw the baby without the bath, out with the bathwater. Whereas this other work that I've been doing with some former students and a colleague is that you just want to shrink the canopy of that former dominance and allow room for others to come in and be part of the overall picture, which is another way of saying we just have to take the dominance of the XYZ coordinate system and sort of shrink it down a little bit and allow for the 60-degree angle to come in and be part. So that you, and this diagram that we're working on shows the both and of those two
Right.
degrees. And I mean, that's so, well, it's easily observed now because of what we've just done. And I was going to say profound, but it's not profound. It's just so integrative that it's and it's an integration that normally if you want, you can't see the trees for the forest.
Right.
And I think what we did was kind of part of the forest a little bit and saw the trees for what they are.
Yeah. Cool. And while you were sharing, I took the liberty to do one more thing, which we did not do, and I will share that with you. And good. I put the circle around the triangle. So
Oh,
now we
right.
have a Renault, we have a Relo tetrahedron now, because
Yeah.
this is a circle around the triangle. So we go back up to
Yeah.
here. And that gives us the opportunity then to change all these straight lines, all the exterior lines into spherical lines, which, by the way, now that we mentioned that, somewhere back here, I forgot about this, but we were close to, what was I close to? I was trying to find, I went to the Rouleau. I guess that was the answer. I went to Rouleau. But what I was looking for was this kind of a
Oh, right.
sphere.
Yes. Yeah.
Yeah, a sphere divided into spherical tetrahedrons.
Mm.
Sphere divided into spherical tetrahedrons. And this, let's see, edges. Okay, there it is right there. This is the guy right here and right here. These two pictures right here and right here.
Oh, okay. Yeah.
So I'm going to take this guy and Whoa, it's that page. We were on that page anyway.
There it is.
Wow. So this shows the spherical tetrahedron that we've just drawn. This shows the place where it fits. And this, I'm going to go. Gosh, I was anxious. I am sorry to capture. I can do these after we leave, or you can, if you're interested, I'll save them all right now. And I'll do my takeaway, and that way you can leave. Spherical tetrahedron from a sphere. And then I'll save this. And then we'll come back here to this guy right here. Which picture do you think is cooler? This guy up here or this one right here is good? Or is this guy the one we want?
Oh, yeah, I think that last one is, yeah.
This guy right here?
Yeah.
All right, cool. Okay. Oh, spherical tetrahedron. Oh my gosh, I evidently have some in here already. I'll call that number 2, and then I'll come back over here and do a search for spherical. Again, if I go back to my mouse, everything's working better. Spherical. And then I'll put it in to see the image. Okay, good. There's one right there. So I could take all
right.
3 of these pictures and whoops. I could take, oh, look, here's the Earth
Yeah.
in a neato thing.
Yeah.
I'll take these 3 pictures and throw them into this page. And but I'm going to do my takeaway. I'll throw these pictures in and make them kind of fit in some kind of order. I think I'll put them in right in here, because this key point about the dysphenoids, this is probably not germane exactly to the topic, so I'll throw it like that. And maybe I can squish that down and get this on 2 pages. I hate it when there's on more than 2 pages. And let's see if I can get all 3 of those in there. All right, I got all 3 of those in there. I'll take the time to modify those. I'll get it prepared and I'll send it to you. Here's my takeaway. Sometimes these conversations are just very, very tedious. And I have to like take a big deep breath and say, okay, let me look at this one more time. And if I don't take that breath and I get caught up in the tedium of it, I'm like your student who hates tetrahedron, then has to go, finds out that they have to go build a bunch of Christmas decorations and end up being stuck with tetrahedron. So if I take a deep breath and just settle in and say, okay, look, let's look at this one more time, maybe I'll see something new. And once again, with you, I saw something new, which is really exciting. And, I get anxious because I'm going, wow, anybody looking at this is way too tedious. This is, I wish I were working 10 times faster. But I'm real excited because that that tri-rectangular tetrahedron, where I came from the 3 90-degree angles of X, Y, Z, and then came up with the ZYX face, the fourth, that came out of my hypnagogia.
Yeah.
So I was excited that we came back at it from another thing, and bam, there we were again, because I did not remember that until you and I went through tediously and rebuilt the whole thing.
Yeah.
Oh, I just love it. And I'm really excited that you allowed me to share about Dr. Faust. And I'm really excited to share that. Oh, you know what? I came up with, we could say God, Jesus, you, and me, but I came up with another triangle, another tetrahedron, and that was God, Jesus, me, and love.
Mhm.
And I think that's the beginning. And if I take love and make it the entire universe, if love is the field upon which the tetrahedron exists, then a perturbation on that field is God, another perturbation is Jesus, another perturbation is you, and another perturbation is me. And I hadn't come to that idea of the field, the sphere, putting the tetrahedron in the sphere of love until just now. So I'm delighted that I got to share my takeaways and gave myself another takeaway. So, wow, Richard, what an honor. Thank you for, I mean, you could say, I'm retired now, I'm going to go do something. But man, you have sure caught the vision and you just keep plugging away, don't you? And you're
Oh,
seeing the
yeah.
fruits of your work just keep coming back at you. How wonderful. I hope that happens to me.
Yeah, no, that's the other thing that's, yeah, quite interesting that you keep seeing some of these things happen, and you don't, I mean, sometimes you feel almost guilty because you can sit here in your easy chair and turn on the machine and you get all this feedback and and they're doing all the work out there, not me now.
Yeah, yeah, that's true.
Uh,
So
but
we get to see the blessing of the folks who are doing the tetramat conversations. That work is coming back to them, commercially
yeah,
successful. Your work continues to come back to you in more than commercial success. I mean, to see all these people taking the ball you threw out there and rolling with it is really cool. So,
yeah, no, that's the really neat, yeah.
yeah,
And the other thing that's happening too, which is has to do with the kind of matchmaking that occurs out of some of these, where, like for example, being reconnected to Yoshimi and John from New Zealand. I
right.
was telling him about
Tetramap.
my work with the domestic abuse group, and so right away we got them. They're now connected,
Cool.
and those two are also working very closely with some Maori indigenous sort of um, uh, programs or prospects. I forget exactly how they're doing it, but
Yeah.
um, and that's always neat when you see other people connect with each other and then they carry on whatever they're going to unfold together.
Right on.
Yeah. So that's great. Yeah, I'm glad.
All
I'm
right.
glad these things happen every once in a while that we end up being the only two on the call, and that's
Yeah.
it feels a bit selfish too, but
Yeah.
thank God they
Everybody
can
else, get
show
out
up.
of the
Yeah.
way. We're going to have a
Right.
conversation.
Yeah. Hey, hey, Joe, I'm glad you're sick tonight.
Yeah. Oh, dear.
Yeah.
And
And we can also
Joe
send
would have,
a thank you letter to Ann's granddaughter and
for
say,
the granddaughter, exactly. And I'm sure if Joe or Ann would have been here, they would have been jumping in on the conversation
oh
too.
yes,
So,
yeah,
but we would have been more tempted to go back to the book. So we'll see.
yeah.
All right, my friend.
Okay,
Always a delight. Talk to you soon.
okay, I
Bye
know.
bye.